Okay, students, in order to implement the gradient descent algorithm, you do simultaneously with me. Open your Jupyter notebook and you have to import NumPy. Before importing NumPy, you have to import NumPy. So import, because we are going to deal with an array only. Okay, so I'm taking two NP arrays as an input to the gradient descent algorithm. X is an on X is one attribute and Y is another attribute. Okay, so we are going to have two different arrays as an input to gradient descent algorithm. So X equal to NP dot array of comma 2 comma 3 comma 4 comma 5. Then we are having y is np dot
So do
array
we
of,
need to create a new file or we have to continue in the simple linear regression?
you better you create a new file. Go with a new notebook. 6 comma 9 comma 11 comma 13. Okay, so simply we are having two arrays, and these two arrays x and
Sure.
y.
You haven't shared your screen yet.
Oh, I'm sorry. Yeah, so I think my screen is visible now. See, you
Yes, sir.
yeah, thank you. So you have to create two arrays x and y. Okay, both should be an NP array, simple arrays, and I'm calling the function gradient descent. Okay, I'm simply declaring a function, that's all. And that function definition we have to write. Okay, this is a function call. So you have to write the function definition. So function definition I'm writing here, definition for gradient descent of x comma y. So here I'm going to write the definition. Before getting to this definition, I would like to explain about yeah, gradient descent, how gradient descent works and all. I'm not getting into detail because already we discussed in the classroom session. Sorry, normal class session. So I'm just brushing up for your better understanding. Okay, see, this is how the gradient descent works. The gradient descent is working based on the mean square error. So we have to fix the, see, if data distribution is like this, we have to find the line which is perfectly fitting in this data distribution. We have to find the line which is perfectly fitting in this data distribution. That is our intention. Perfectly fitting in the sense with minimum error, with minimum mean square error, with minimum MSE. MSE is nothing but mean square error. With minimum error, we have to fit this particular line in data distribution. That is our intention. So in order to do that, we are using gradient descent algorithm. Gradient descent algorithm only choosing the proper line. Okay, multiple option is there. See, I can draw a line like this. I can draw a line like this. I can draw a line like this. Like this I can draw. Like this I can draw. Like this I can draw. I can draw. I can have n number of option. Okay, how can I evaluate which one is best? Which is having the minimum MSE is better one. Okay, how do you find that minimum, the line which is having minimum energy? For that only we are using gradient descent algorithm. Then only we can able to solve the regression problem. Okay, so now see in this three-dimensional space, we are plotting M intercept. I mean M, B and MSC. B is nothing but an intercept. Can write it as B also. So M, B and MSC we are representing. See here, M is nothing but a slope. So initially MSC is high. Okay, initially MSC is high, then MSC is getting reduced, getting reduced, getting reduced. Then at some point of time, MSC is reaching global minima. After reaching the global minima, MSC will get increased. After reaching global minima, MSC will get increased. Okay, so we have, our intention is to find this global minima. Once MSC reached this global minima, that in that particular point we have to take the slope and intercept. Okay, where the MSC reaches global minima, in that particular point we have to, in that particular point we have to take slope and intercept. Okay, that is our intention actually. Got the point? So that's why we are using gradient descent algorithm. Okay, the gradient descent algorithm only finding this minimum MSC, and that in that particular point it is taking the slope and intercept. So MSC, intercept and the slope, if we plot these three in a three-dimensional graph, we will get bowl kind of shape. Okay, we will get bowl kind of shape. So the global minima is the bottom of the bowl or center of the bowl. Okay, see now if the curve is like this, okay, if the line is like this, if the line is like this, MSC is high, MSC is high, here MSC is less, here this area is sensitive, here MSC is high, here also MSC is high. Here MSC is definitely high. Here also MSC is high. This area is only a sensitive area. So here only we have to choose appropriate global minima. So this area is sensitive area. That area only, this bottom area. Here only we have to be careful in finding global minima. This there only curve comes. Okay, so we will see how gradient descent algorithm find that global minima and solving this problem. See, when we plot this MSC and M, it is starting, see, with respect to MSC and M, see, we are starting from here and coming down, sorry, coming down, coming down, coming down and reaching, see, it is starting here and coming down and reaching global minima and going up. Okay, so for the intercept also, if we put MSC and intercept, initially MSC is high, then it is coming down, reaching global minimum and going up. Okay, it is working like this. Okay, so this we have discussed already, the small steps and greater steps, where we have to take small steps and where we have to take, a bigger step. Okay, see here, if you take bigger and bigger steps, see, you may miss global minima. See here, if you take bigger step, you may go here. So if you go there, you may miss the global minima. So here you have to take smaller steps. Here you have to take smaller steps or baby steps. So in order to take smaller steps, you have to identify the direction of the curve. In order to identify the direction of the curve, you have to find the slope of a point. Okay, so how we are dealing with slope of a point and how we are solving this problem, that we are going to see now. Okay, see, so here, so in order, here we have to find the direction of the curve. So in order to, why we are finding the direction of the curve? In order to find the global minima, we are finding the direction of the curve. So in order to find the direction of the curve, we have to find the slope of a point. Everyone know the formula to identify the slope of a point. See, slope of, sorry, everyone know the formula to identify the slope of a line. Slope of a line is nothing but change in y divided by change in x. This everyone know. Change in y divided by change in x. See here, 3 by 6. Change in y is 3, change in x is 6. So 3 by 6, 0.5. Okay, this is the answer. Okay, but slope of a point, finding slope of a point is difficult. So if you use the same formula, change in y divided by change in x, you will get 0. So this is not the perfect slope. So in order to find the slope of a, in order to find the slope of a point, you have to go with, you have to go with what? You have to go with differential calculus. We have to use differential calculus in order to find the slope of a point. We have to use differential calculus. Say for example, if your curve is x square, okay, if your curve is x square, 2x is the slope of a point at any x point in that curve. Okay, consider x square. X square is the expression for parabolic curve that everyone know already. So in this x square, see, in that x square, consider this x square curve, parabolic curve. So what will be the, in this x square curve, what will be the differential calculus of x square or differentiation of x square? 2x, right? Yes, 2x. Okay, so 2x. Say for example, here if you substitute 2, so here you need to find, here you need to find the slope. So x value is 2 here, so 2 into 2, 4, slope is 4. In x value 1, here you can keep a point and you can find slope. Here slope is 2, here slope is 4. If it is 3, here in the sense 3, say for example 2.5, 2 into 2.5, 5 is the slope. So likewise you have to identify the slope. Once you identify the slope, you can able to understand whether it is going straight or it is turning. You can able to identify the direction of the curve. So here it is a parabolic curve, you can able to say direction is this, but in normal, in real time, you have to find slope of a point in order to identify the direction of the curve. Okay, that's what you need to do. Now just look here. See, if your curve is 3x square, sorry, x cube, 3x square is the differential derivative of x cube. Okay, so by this you can able to find the slope of a point. So in order to find slope of a point of a single variable expression, you have to apply derivative. But in our case, we are not dealing with single variable, we are dealing with multiple variables like f of x comma y, x comma y for x cube plus y square. Here you have to apply partial derivative. So partial derivative is nothing but dou f divided by dou x. So 3x square plus 0 equal to 3x square. This is partial derivative with respect to x. This is partial derivative with respect to y. So two variables are here, x and y. So partial derivative with respect to x we have to find. So partial derivative with respect to y also we have to find. Okay, these two we have to find. See, now what equation we are using? We are using this equation, MSE equal to 1 by n into I equal to 1 to n yi mx plus v. See, this is the MSE equation. This is the MSE equation. Okay, so this is the equation for MSE. See, this is the equation for MSE. If you want to identify the direction of your curve, okay, if you want to identify direction of your curve, direction of this particular curve, see here, it is represented a parabolic just for understanding. But if you want to really understand the curve in the sense, you have to apply partial derivative on this particular equation. You have to find the slope of a point. In order to find the slope of a point, you have to apply partial derivative on this curve expression. This is the curve expression. You have to apply partial derivative on this curve expression and you have to find the slope of a point. With the help of slope of a point, you can able to identify the direction of the curve. Okay, see here. So partial derivative with respect to m, this is the formula. Partial derivative with respect to b, this is the formula. Okay, this way you have to identify. So these two formulas are taking vital role in gradient descent algorithm. So these two algorithms are partial derivative of this MSE. Okay, you have to apply differential calculus on this. So partial derivative on this equation is these two equations. Okay, so after that, see what we need to find is after this, see here m and yeah, look into this. See here what we are doing is, yeah, see, so this is actually first iteration and this is second iteration. We have to do it iteration by iteration in order to find the global minima. First iteration in the sense we are choosing one, we are taking one line and finding MSE, intercept and M. And after that we are taking second one, see here. First we are taking the line like this. We are taking the line like this and finding MSE, M and intercept. And keeping line like this and finding M, MSE, intercept. Like this we are doing up until otherwise we are finding global minima. So now we have to identify the direction in each and every step. See, in this first step, this is iteration 1, this is iteration 2. So So the formula formula here we are using is, see here, m with respect to m and with respect to b we are using. Okay, I'm showing this to you. See this, I'm showing this to you. See here. So in first iteration of m, sorry, second iteration of m is first iteration of m minus learning rate into partial derivative of m. Partial derivative of m formula we are having here. We are having here. Okay, this is partial derivative of m formula. And in second, the third iteration, m equal to second iteration m minus learning rate into partial derivative of m. For b also same. Okay, second iteration of b equal to first iteration of b minus learning rate into partial derivative of b. This formula also we have. So likewise we have to move the curve and we have to reach the global minima. So this is the formula. Here the learning rate, what significant impact this learning rate is having, how this learning rate influence the curve, and how this learning rate influences the finding global minima, everything we will discuss. Okay, while implementation. Now straight away we'll get into the implementation. I hope you don't have any doubt in this theoretical explanation, right? Yes, students, any doubt? If do you have? Yes, Parth, Deepsha.
No, sir.
Okay, good. See, now look into this. So we are having array, we are having function. I'm going to implement. So first m current and b current equal to 0. I'm initializing m current and b current equal to 0. I'm putting 0. Okay. So this m current and b current, why I'm putting 0 is, see here, this one only m current and b current. See, m current is the current iteration. Next iteration, every iteration we have to, initially we are declaring this m current and b current as 0, and each and every iteration it will change, it will get updated. Okay, so iterations iterations I am keeping it as 1000. So I'm having 1000 number of iterations. Iteration is nothing but number of loop execution. So we will see what we will get if we change the number of iteration and all, and what we will get if we increase the number of iteration. Everything I will show it to you. So n equal to length of x. So length of the array, that is nothing but an n. Okay. Then learning rate we are having as 0.001. Okay, so what is the significant impact which learning rate gives in our code, that we will discuss. Why I am choosing this learning rate as 0.001, I will explain. Okay, once the execution has been done, I will explain everything. Now don't worry about that. Okay, so now I'm getting into the iteration or loop for I in range iterations sorry iterations. So here I'm having y predicted equal to m current into x plus b current. Okay, see, this is nothing but y equal to mx plus c, nothing more than that. Y equal to mx plus c, that's all. Okay, so this m current and b current we have to keep on updating in each and every iteration. So before that we have to find md, partial derivative with respect to m and partial derivative with respect to d. That is here, partial derivative with respect to m and partial derivative with respect to b. This formula only we are going to implement here. Minus 2 by n into sum of x into y minus y predicted y predicted partially with respect to b equal to minus 2 by n into sum of y minus y predicted. This we have to find. Then m current equal to m current equal to m current minus learning rate into md. See, once we found partial derivative of d and partial derivative of partial derivative of m and partial derivative of b, we can able to find m current. So m current is this formula only. Okay, this one, m minus learning rate into partial derivative of m, partial derivative of b, the same. So, okay, same b current equal to b current minus learning rate into learning rate into BD. Okay, then here, so that's all, our implementation done. So we have to print m current we have to print, that is m value, and we have to print b current, and we have to print the cost also. Cost is main, but cost we haven't calculated, so print cost is nothing but an MSC. So MSC we have to calculate. So based on that only we are finding global minima, right? So that is nothing but a cost. So what is the formula for cost? This is the formula. Everyone know, right? Formula for cost is this one, MSC. So this is the MSC formula. This formula we have to, calculate. Okay. So for that, cost equal to 1 by n into 1 by n into sum of true for value in y minus y predictor minus y predictor. Okay. So this we have to implement. Okay, cost we have calculated. See, square we have done for this. The same formula we have implemented. So let me execute this. See, I'm getting an error. Gradient descent is not defined. Yeah, now it has been executed. Listen to me. I would like to give a space for each and every iteration of selection. Then only we can able to differentiate how, oh my God. Okay, see, now the initially cost is 86.4. Okay, see, like this. It is then it is getting reduced 82, then 78, then 74, 74. Likewise, it is getting reduced, right? 768, 64, 61, 59. See, it is reducing. So we are going in right track. We can able to understand we are going in right track. See, our intention is to reduce the MSC. MSC should be initially here, then it should be reducing in order to reach global minima. If it is reducing, we can able to understand we are going in a right track. So finally, after 1000 number of iterations, so he see here 4341 0.4339. So only little bit difference. very small difference is there. You can stop here itself. If you want, you can stop here itself, and you can consider this as a global minima, and you can take this m value and b value. If you want, according to your application, according to your context, if you want, you can stop it here. Okay, so that you have to decide where you have to stop. Otherwise, if you want more clear answer or more precise in the sense, you can go with 10,000 number of iteration also. If you go 10,000 number of iteration, you will get more precise value. You will get more precise. It is still executing. See, after 10,000 iterations, see here 0.1406 up to this same value 0.1406, 0.1406. See, okay, so you can stop it here. That is up to you as a data engineer, as a machine learning engineer, as a data scientist. You have to decide where you have to stop according to your application. Okay, now yes, as of now, any doubt? Yes, I will tell what is the role of learning rate to you. As of now, any doubt? Yes, students. Is it clear now, Parth? Is it clear now?
Yes, sir.
Okay. When you're having voice problem previously?
Yes, sir. Few minutes back it was not clear, but now it
Oh,
is clear.
okay. Thank you. So yeah, clear with the concept, the execution. Do you understand what I'm doing? Yes or no?
Yes, sir.
Okay. So I'm giving this code to you. You have to execute it and you have to show me the output to me. Okay. Now listen to me. I will tell the role of learning rate. See, instead of the learning rate 0.001, I am putting 0.8 and I'm putting only 10 iterations. 10 iterations. See now, see the answer, see the result now. 86 2754488. See, it is getting increased. MSC getting increased. Okay, MSC is getting increased in the sense there is no meaning. See, instead of coming down, if it is going up, in the sense, what is the meaning in that? There is no meaning in that if it is going up. So we are not in the right track. You can able to analyze, or you can able to sense you are not in a right track. So that you have to analyze and you have to fix. It is absolutely a trial and error method. Okay, and I'm putting 0.001 instead of, I reduced 10. Now see, it is reducing like, yeah, 86, 82, 78, 74, 71. See, it is taking longer step. So if you go in this way, you may miss global minima. It is longer step. Okay, so I'm ending up with 0.001 because okay, the number of iteration also. If you want more precise, you can go up to 10,000. That is up to you. This way you have to implement and you have to find. Yes, got my point? Yes, any doubts? Any doubt? Yes, students. Arun Singh, have you done? When?
Yes, sir. I was completing side by side
Good,
with
good,
you.
good, good, good. Then share the screen. Can I stop my screen sharing?
No, sir. I can't share because I have a very less data left today, and if I connect it with my laptop, my Windows update will
Okay,
just
okay, okay, okay,
take
okay,
my.
okay.
I can turn on camera and I can show you.
It's okay. Okay, yeah, yeah. Please. Yeah, good, 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 good. Very good. Yeah.
Sir, can I share?
Yeah, please, 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 path 9221 TC3.
Sir, is it visible?
Yeah, 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 absolutely.
Done 10,000 iterations for a.
Good, good, good. Okay.
Sir, now can I stop sharing?
Yeah, yeah.
Okay, sir. Thank you.
Very good. So if you want to explore more, you can import CSV file data and you can implement, can do further if you want. So that's all about to gradient descent algorithm. So what about others? Only DIPSA is here. DIPSA, have you completed?
Sir,
Yes, yes, Parth.
sir, means how many practicals we have completed?
Actually, we have completed as of now two, and the other batches have completed three up to multilinear regression. So
Sir, just because we did not have one lecture that was on 26th of January.
yeah, yeah, we
That is
missed.
why we are lacking behind.
Yes, yes, yes. That
Hmm.
we can cope up, that we can do it
Yes,
soon.
sir. Yes, sir. We will cope up means in one lab we can do it. Do it means in next
Yeah,
lab
yeah.
we will.
Because that multilinear regression we have almost completed in this class itself. We are going to do with some other data set, bigger data sets. That's all.
Okay, sir.
After that, we will get into other experiments. Dipsa is here. Okay, Parth, Dipsa, and Arun Singh. Only three are present. Right? Parth Rai, Arun Singh, and Okay, 40, 155, 180. Yes. 40, 80, 155.